Hi everyone. Yeah, I wanted to maybe do a little bit of a different type of video, more like walking through some code, which is, maybe a little bit of a different type of content than what I usually do for quantum computing or other types of errors, because across many videos in my channel, I've talked about like several instances or use cases of algorithms, and a lot of times I've alluded to or demonstrated different aspects of my code that I've used for running the simulations, but I haven't really ever showed something that's completely, more or less what I exactly use. And I just wanted to preface this by saying that I did do a lot of this work, when I was a master's student at Cornell University, and also following my undergraduate degree there. And I also even did some of this stuff, on my free time for fun when I was in industry for some time. And I just wanted to say that there are significant parts of this code that I've completely deleted and cut out of this segment because it's not mine, and I'll kind of explain how I made use of that code in portions from what other students did that took them a lot of work to do, that allows someone to have an idea about how to perform time evolution with Python for quantum computing. And as I've alluded to in the title of the video, pretty much what I'm going to make use of is just pretty much looking at Cirq, which is an open source package provided by Google Quantum AI. And like I've talked about in my different types of presentations, this type of open source package that's offered by Google Quantum AI, it really has the impact of being able to provide some type of ideal noiseless simulator for the wave function of some quantum state that you want to look to time evolve, and how maybe the people at Google Quantum AI would expect this to play with near-term devices that they currently have, like either in their labs in Goleta and Santa Barbara or other types of places. And it's also going to rely on like some basic Python functionalities, like basically trying to store a bunch of numbers in arrays because you're trying to obtain some type of measurement or readout from the solution at different points of a time evolution, as well as given by the fact that you have to pass these solutions to plotting functions like Matplotlib or Matplotlib3D. But to have an idea about what type of cost function you want to optimize, as well as different types of optimizers that you'd like to interface, you kind of have to do a bit of reading and looking around in to determine which open source packages would be able to be of the best use for you and your purposes for these types of numerical simulations that you're trying to perform. So again, with the exception of the code for the ansatz, which is done by another student, Abhi Sarma, who he's now a graduate student at somewhere else rather than Cornell. I'm not going to reproduce his code because that's not something that I used, but I'm going to demonstrate and maybe just allude to parts of my code where I use functions from his code, and without explicitly defining everything that he does, which takes a lot of work, what he did. I'll try to allude the viewer to how one could maybe make use of some initial state preparation routine that's used in quantum computing to perform time evolution. So, and just to begin, I think that one of the things that's really helpful is obviously not everyone's code is perfect. It'll like have some things here and there that are superfluous or aren't necessary. But in the case of my code, I just really think it's helpful to, highlight like what types of things you need and, to even get started and going, because that's really the most annoying part, and like debugging basic things when anyone ever starts to make use of any type of code, like any type of code that I've used for like across my industry positions, even though I wasn't in industry for that long. And what you really have to make use of is, you have to make use of some circuit diagram, which is an object that's significantly manipulated in quantum, in the Cirq package from Google Quantum AI. And what this has the impact and the effect of doing is that this package allows for someone to basically perform time evolution on some number of qubits. And the qubits are initialized in one area of the quantum circuit diagram, and from this initialization in the zero state, it's time evolve forward under some type of unitary transformation, which is just given by a matrix such that the matrix times the conjugate transpose of itself is equal to the identity matrix. And this is just a fundamental tenet and core principle under for time evolution in quantum mechanics. And in addition to importing Cirq and QSIM Cirq, which is another type of auxiliary package which is used to perform time evolution on a wave function when we're looking to perform some type of quantum computing numerical simulation or some type of virtual experiment, whatever you want to call it. You pretty much also have to think about how classical components of computation would fit into the play with the quantum algorithm. Because with the quantum algorithm, when you're looking to perform time evolution, the whole hallmark and primary feature and characteristic of a variational quantum eigensolver and generalizations of the variational quantum eigensolver is given basically by the fact that you have to still make use of classical computation, even if you're trying to do a quantum algorithm, whether you'd like to admit it or not. So I think that that's demonstrating part of the reason why, as to why, even though many people have still been expressing optimism for quantum computing, it's still very much in its infancy, and it's still very difficult to determine which types of near-term applications would be within reach for, many types of companies, even industry leader players, which I'm very sure they're aware of, because like Google Quantum AI, through their groundbreaking work in progress in trying to demonstrate different quantum supremacy tasks that could be executed in polynomial time, which could lead to an exponential speed up in runtime from whatever a classical algorithm could do on a quantum computer, they're still pretty much always having to try to figure out about whether there's any classical computing competitor or progenitor or something that could come out from a classical computing routine that could still outperform their quantum algorithm, which would then raise some types of concerns or maybe difficulties for the quantum supremacy claims that they've raised. And what has to pretty much come into play through my implementation of the quantum algorithm is that we have to implement a CNPU. It really stands for a quantum nonlinear processing unit. And as we've been saying here, this particular function in the Python code is really given by the motivation that it appears in a paper from Lubash et al., in which they had performed time evolution for some, proof of concept time evolution experiments for the nonlinear Schrodinger's equation and other types of equations, which, my principal investigator at Cornell, he mentioned that it would be very interesting to determine whether this type of, time evolution experiment would be interesting to scale up for, additional, other additional PDEs, which may have many more nonlinearities at play, which govern their dynamics. And, we're not really looking at things from a rigorous perspective because, when you're looking at a time evolution experiment or performing some numerical simulation to see if this quantum algorithm that I'm going to describe to you in more detail, it's going to actually be able to terminate within polynomial runtime while still giving some approximation of the solution, you don't really know which types of initial conditions or which type of ansatz, as we call it in quantum physics and quantum computing, are going to end up working. And that's really what happened to me because I had to perform, as anyone would, a lot of, different classes, so to speak, of initial conditions for determining what would end up working the best, which would reflect on some potential positive characteristics and positive beneficial uses in the future of this type of quantum algorithm or of the variational quantum eigensolver in general. And why the CNPU comes into play is because it's pretty much directly given by making a bunch of quantum circuits, constructing them explicitly within the code from Google Quantum AI and their Cirq package. And again, that's why I thought that having this type of visual of me actually walking through the code and discussing how different parts of the algorithm relate to the code, it's really helpful because Google Quantum AI, they had a very helpful tutorial about what Cirq is used for, namely their open source package, but it's a very short tutorial and it may not, show all of the potential uses or applications of this package because, they're pretty much talking just for 2-qubit quantum circuits. And for sure, that's the most basic building block for quantum computing, but it's obviously not the only type of situation because you can look at circuits with many qubits, like even hundreds of qubits, and even though maybe right now in this time and age it may not be very realistic to be able to time evolve or perform time evolution on those circuits because the noise would completely prevent any meaningful measurement from being obtained from the readout, you can at least do it without noise to first see how different parts of the code would work and how you can add on further complexity. And this is really given by the fact that throughout all the code, psi is just the quantum state corresponding to the solution of to the solution state, or the solution wave function, as you could call it, for some PDEs. So whatever PD you want to think of, even if it's something from the 15 PDEs that I didn't do yet in that paper, in that preprint that I posted a long time ago from 2022, you can still pretty much look how to make use of Cirq, in which you have to look at, initializing, as I say here in the first line, some number of grid qubits for some specified range, which is specifying the depth of the quantum circuit, as well as all of the total number of positions for the qubits that you're going to initialize in the zero state. And then what you have to do, which is just pretty much relating to the quantum circuit that's obtained from the Lubash et al. Paper, is that they have a bunch of gates in their quantum circuit architecture for Hadamard gates, as well as other types of gates, like adder gates, which are all relating to being able to perform time evolution on some wave function. So what you basically have to do for the first step for define the quantum nonlinear processing unit is that you're specifying the number of qubits, the old psi params, which are the initial psi parameters that you're using to start your simulation up on, and then you also have to initialize the psi params for the solution state of the wave function that you want to time evolve, as well as what would be the new psi params for the solution after you perform a time evolution step. And having this type of construction for the quantum nonlinear processing unit is really going to help us, because it's pretty much letting us be able to perform this optimization through quantum and classical computation potentially thousands of times. And as anyone could see, from some of the solutions from the PDEs that I simulated for like wave propagation, I ran some of those time evolutions for like, 10,000 or 20,000 steps on my laptop, which really can take a long time. And you need to have some stable type of routine in which you can set some reachable optimization or cost, cost or overhead with regards to the optimization, that it can then repeat thousands and thousands of times, or maybe even, if you really can run each time optimization step very quickly, you could even do it millions of times. Say if each optimization step takes like a millisecond or a fraction of a second to do, which would then be able to help you generate some type of candidate solution for some PDE or nonlinear problem that you're interested in, like in the words of Lubash et al. And each one of these portions of the definition of the quantum nonlinear processing unit is given, as you can see here, by a bunch of nested if statements. And all these if statements, what they have the effect of doing, like how I alluded to, is that because we specify n, which is the number of qubits in whatever quantum circuit that we want to time evolve, we specify the expectation value that we want to perform the time evolution to when reaching the quantum nonlinear processing unit for each one of the registers of the quantum circuit that we first initialize to the zero state. And what this has the effect of doing is that it's pretty much allowing us to form a representation of the cost function, because on one side, on the classical optimization side, we have the cost function, which is relating to what we want to optimize over, and we're going to analyze with classical computation and classical optimizers, so that we can perform time evolution on the quantum side of things. And you can see that I chose this particular PDE in particular because it really exhibits a lot of variety for expectation values that you can have in terms of the quantum circuit. Like you can even see here for the 13th expectation value that I have A dagger times A times psi. I have a lot of other expectation values for A dagger times psi nu, maybe relating to the fact that in some instances from nonlinearities in a partial differential equation, you may have to perform 2 time steps forward, which is relating to also having to also having to store some variational parameters, which are relating to the parameters which are inherent in the wave function for the solution after 2 time steps of evolution. And in particular for this, as you can see from the title of the script, I called it the BL, cost function, because it's for the Benny-Luke equation. This cost function was probably one of the most longest ones that was given on the preprint that I gave, in which it was a couple pages long to write it out. And a lot of times, like from the cost functions that I obtained in that, I obtained some type of analytical approximation from in that preprint that I was using to perform time evolution on for, demonstrating some proof of concept for noiseless quantum computation, it was really relating to the fact that, there are so many complexities and so many nonlinearities that arise when when you represent nonlinearities from, statements, of the solution, as well as other types of actions that you can take on a solution to a PD or a nonlinear problem of interest that arise when you map these into operators in the Hilbert space, and how a lot of these cross terms arise from just having to multiply a bunch of terms together basically to get the cost function. And, more or less, probably the most complicated cost functions that I had in that preprint were relating to wave propagation, probably. And those were probably also the most involved numerical experiments, because those types of numerical experiments, it took like a while, at least a few days, for it to run and to generate those solutions, like how I said, how I ran it on my hardware. And, on top of that, like how I had alluded to at the very beginning, you just have to make sure that you have, Cirq, which is the open source package from Google Quantum AI. And despite the fact that I didn't run the time evolution on other packages rather than Cirq, you can pretty much think about translating any of these types of instances for obtaining some type of time evolution per se, in Qiskit, which is IBM's, proprietary type of quantum computing package, by like translating each one of these lines so that you have some type of representative quantum circuit for whatever, near-term devices they have, and how that could actually help you perform time evolution, for maybe if you wanted to like test a proof of concept out on their cloud devices, or also cloud offerings or cloud device, other cloud offerings or cloud devices from other quantum computing providers. And as I said, the fact that the Benny-Luke cost function, it's a very complicated, yields or leads to a very complicated definition for the quantum nonlinear processing unit, because a lot of these terms, as you can even see, I pretty much like made circuits for being able to approximate several types of products of expectation values that are given by, making use of, as I said, the Hadamard gate, which is given on a qubit, as well as also appending to the circuit some ansatz state, which again, like I said, I'm not providing code for the ansatz because I didn't do that. I'm just showing how we can make use of the ansatz state and how that would come into play from different arguments that are given in the quantum circuits that we can construct for the quantum nonlinear processing unit, which is helping us perform some desired optimization routine on a cost function that we're initializing at some state in Hilbert space. And as we keep on going down in this quantum nonlinear processing unit function, we can see that there are hundreds of expectation values that I coded in. So that's why I think it's like really helpful to see about how one would construct these quantum circuits and how really powerful the Google, the Cirq open source package from Google Quantum AI is, because in this one, I was able to perform time evolution on a quantum circuit with 161 expectation values that I was able to code in from the quantum nonlinear processing unit. And it again shows that, at least from the noiseless type of perspective, when we're performing quantum computation, the framework that's provided by Lubash et al., it's really a powerful framework that is a lot more robust than just the proof of concept type simulations that they ran for a few qubits on the nonlinear Schrodinger's equation and on the Burger's equation, and in particular how you can really generate quantum circuits and try to perform noiseless time evolution as an initial proof of concept from hundreds of expectation values, which is definitely the case in this place. And even from to perform a lot of different types of time evolution experiments for quantum computing, that can even be done by like taking the whole quantum nonlinear processing unit that I showed to you guys here with all the 161 expectation values that I explicitly coded in from those different circuits, and being able to look at different types of maybe more complicated or even less complicated circuits that you can use for studying either a more restricted narrow set of nonlinearities, so that you can determine whether there's maybe a smaller type of circuit that's more parsimonious that could be used to perform time evolution that would then allow you to still be able to obtain some type of readout that would be beneficial or informative for your types of purposes in determining whether this quantum algorithm can provide some potential speed up in runtime. And rather than the quantum nonlinear processing unit, we also have to define the cost function. And the cost function, as you can expect, it's still a very complicated expression because it's just basically a function in which you have to return this number. And this whole highlighted portion is the whole thing that I coded up for the cost function after double checking many times from the cost function that I analytically derived in the paper. And obviously, because a lot of people, they don't really include their code for quantum computing in their papers or things like that, it can just be really difficult to understand all of the aspects that go into a project with regards to the coding and how it relates to the mathematical side of things. It's an applied math problem because it's not a pure math problem. We're not really proving anything about, with regards to what class of initial data is going to lead the quantum algorithm to maybe be able to perform some polynomial or exponential speed up in runtime in the absence of noise. And with that being said, what we always have to specify when we're returning the cost function is the square of the variational parameter as given by the fact that after the square of a variational parameter, which is representative of some initial state that we start out in the time evolution as given by this part here, we have to have all of a bunch of other terms within that are embedded within this return statement, which are either relating to prefactors or different expectation values from the quantum nonlinear processing unit that I defined in the function above it. So that's how the quantum nonlinear processing unit, it relates to the code for the cost function because you make use of either maybe some prefactors or the time length for the time evolution that you want to perform from the solution state of the wave function that you initialize that's going to be initialized in some type of zero state or some type of ground state at the beginning of the time evolution from the quantum circuit, which is then going to be time evolved forwards according to this cost function. And again, like I mentioned, that's just why it's really interesting about how much prospects and why I thought it was even informative to talk about this type of these types of numerical experiments in Cirq, because it really demonstrates how robust the open source package in this open source framework from Google Quantum AI is. Because after all, they're trying to think about how to construct and synthesize a quantum computer that can maybe operate on the order of millions of logical qubits at the same time. So they're just trying to demonstrate that there's some type of open source package that can be able to perform noiseless time evolution as an initial starting point that can be very encouraging, that they could then look to further, add complexity to in the presence of noise. And now that we have the quantum nonlinear processing unit and the cost function, as I've been saying for the Benny-Luke equation, which is, pretty much probably the longest cost function throughout that 2022 preprint that I've been alluding to, that I gave from the McMahon lab, we can also look to perform time evolution, in which we pretty much have to be able to, initialize cement the array that we're going to pass off all these results to, which will then allow us to basically, basically perform some time evolution and generate some type of numerical approximations from different initial conditions that we can pass. And like I mentioned, there's a lot of code that some of my other colleagues in the lab, they really tried out, to experiment with, and some of them, they didn't, they maybe tried out several different ansatze or different initial positions that didn't end up working. But that's unfortunately very much the name of the game for quantum computing, because when you're trying to determine which classes of initial conditions work better, sometimes some initial conditions may work great more beginning, near the beginning of the time evolution, but they may not lead to very interesting dynamics or long-term behavior or, any types of interesting, or unexpected nonlinearities later on in the time evolution. So this is really going to show about, it's very much a play, it's very much like you have to plug in different types of initial conditions and run the simulation and see what types of solution curves will be generated from the time evolution. And that's pretty much what we do here. As I'm saying, we initialize the empty solution arrays, and we just initialize a bunch of them because we want to perform, time evolution on a wide variety of initial conditions for determining what would the expected output be. And here's where we actually start the time evolution. And again, like I had alluded to, there are probably some unfamiliar words that didn't end up coming up from some of the code earlier because, like I said, I deliberately deleted some of that because I wanted all of the code that was shown in this presentation to belong to me pretty much, in which I was beginning to describe how I made use of the Cirq open source package, as well as being able to perform time evolution on this and being able to establish a connection with classical optimization routines through the cost function, which is just basically, defined in terms of all the expectation values that are given in the quantum nonlinear processing unit. And this is just basically given by the fact that, as we show here, we're performing just a time evolution of 500 time steps. So we can imagine that we can make each one of the time steps of the evolution last for however long we want. And then we have to specify the total number of space uh, grid points in the space, which is given by 2 to the number of qubits. So however many qubits we have in the quantum circuit, the space of X that we're going to range over in the time evolution, it's 2 to the number of qubits, as well as given by the fact that we're passing some argument which is given by old params, ZGR params. And again, the ZGR params, it's given by a function that was written by one of my colleagues that he wrote for everyone in the group so that we could play around with it and experiment around with it in the lab, because the ZGR params is given by the fact that it stands for Zalka, Grover, Rudolph, Ansatz, if I remember all of the names correctly, which is given by the fact that it's given by an ansatz which has been identified from many people in the field of quantum computing as being very promising and interesting with regards to being able to perform reliable time evolution, as well as being able to look at different favorable initial conditions in Hilbert space under which maybe the quantum algorithm could be able to initially perform some computational advantage in runtime, which would then help us envision or realize different types of applications that could be used for the quantum algorithm for other types of nonlinear problems. And then there are also some other more technical functions which my colleague wrote, which is relating to the fact that I had to basically make use of and manipulate these functions so that after each time step of evolution, I can update whatever parameters are given in the solution state wave function so that we can then continue this optimization routine on the classical side and have a connection with the quantum side in terms of the solution state wave function and how that's relating to the types of measurements that we would like to extract from our system from some time evolution experiment over potentially thousands of steps, like I described in the case of solutions to the Kamasa-Home PD, which is describing wave propagation and other fluid type related phenomena. And then just for my case, just to make things easier, as I said, just so that I can see the output in the solution approximation at each time step of the evolution, I just wrote in the code, some simple print statements so that every time it goes through some fixed number of time evolution or some iteration, it's going to print out the solution approximation so that I can just make sure that if I pass the quantum algorithm, this extension of the variational quantum eigensolver, some type of non-zero initial condition for the state, that it would be able to continue producing some non-trivial, non-zero value for the solution, which would be indicative of some non-trivial dynamics occurring within the nonlinear, from the nonlinearities of the PD as we're performing the time evolution. And this is pretty much getting more to the end of the script, in which there are undoubtedly many scripts for other PDEs that I've given that are a lot more confusing or are a lot more complicated and intricate than the script I've been showing here. But this is pretty much just giving an idea, as I said, a type of bare bones implementation, so to speak, about making use of time evolution through quantum Cirq, and basically being able to make use of some type of optimization routine in which you pass some parameters the budget of the optimizer, namely how far can the optimizer run to find a global minima for a solution, and how this would actually relate to plotting the solutions and being able to form some type of visualization about dynamics of PDEs. And how this is relating to the plot functionalities, like I said, is that because you're just pretty much always trying to look to plot, however many time steps you had, like npi numpy.linspace, so 1 by 500 by 500, because in this case, we're performing 500 time steps of evolution. So there's going to be solution arrays with 500 entries, which are each given by the value of the wave function at each time step of the evolution. And then you can basically plot, like how you can see from different figures in my paper, the solution curves in different colors so that you can compare the dependency of the values of the solution, and hence, gain some type of idea about the time evolution depending upon, what types of initial conditions did you pass to the solution in the first place. And then you can pretty much also label the X and Y labels from the solution approximation and the time step number, which doesn't really come to, at anyone's surprise at all. And then you can pretty much be able to, put favorable simulation results into some preprint or to some paper by saving the results from the graph to PDF format, which you can then, put into your project and overleaf, or, any other type of document if you want to send someone your simulation results for gathering their thoughts or determining whether the time evolution and the expected solutions that the quantum simulator output when you're performing this classical quantum optimization feedback loop were actually performing as expected. And yeah, that's pretty much like demonstrating a lot of the bare bones, because you can just see that I made like 7 figures. You can label each one of the figures so that when you're plotting them, Python and Matplotlib or Matplotlib 3D for three-dimensional solutions, it doesn't necessarily really get confused about which types of solutions or patterns you're trying to overlay on top of each other. And then it can just pretty much generate a whole bunch of individual plots that are separate from each other that you can then use for analyzing different types of initial conditions. And you can see that I have, Nevergrand optimizer results, which is an open source optimizer given by Facebook that is a really good optimizer. I also made a lot of use of infill optimizers, in which you can pretty much look at how I did here, defining some solution state wave function from some initial time evolution step, and then being able to further perform time evolution on this wave function, which would then allow us to potentially extract some measurements from the quantum algorithm, which again is a very good or beneficial place for us to start our investigation of quantum algorithms from. If we're just looking to perform time evolution without noise. And pretty much the code from this point on, it's pretty much similar to what I already showed you before, because after I perform this time evolution, I just have a bunch of more code that leads to the end of the script from what I showed you from what I did, which demonstrates, like ways to either, save the figures into PDF format from different combinations of solution arrays that we did. So yeah, thanks for watching. I just thought that this would be helpful to talk about, and further complement some content that I've been doing on quantum computing, and how really you can think about a lot of the core ideas of time evolution and quantum computing for more of a script format. Because I know that, when I initially started this type of research, I wasn't obviously thinking about things in terms of this Python script or different types of Python scripts, because I have like 60 of these. I have a lot of these that are used to accommodate several different types of nonlinearities that appear in different types of PDEs that I was performing time evolution of. But it really goes to show about different types of ways that you can perform numerical experiments. And maybe for people that think more easily in code and, can make connections with mathematics from that, then it can kind of help give you an idea about how I organize the code into those within those different open source packages like I mentioned. And thanks for watching.